I'm going to present this work. This is a joint work of a team of 9 people, which come from all over the world. We got people from Johns Hopkins, MIT, University Toulon, Le Mans University, and University of Wrocław, of course. So how this collaboration started? I should give credit to JSOLT. So you might be not aware that every year for like the past 20 years, there's a JSOLT workshop going on somewhere in the world, typically in Boston. JSOLT is like a 1 month, month and a half workshop that gathers teams of people that work on some developments in NLP. So you may probably heard of the Moses translation toolkit, Kaldi speech recognition toolkit, Zero Speech challenges, and more recently, Giant NLP benchmarks. These all started during the workshop as projects of different teams. So this is my team. This is like the 9 people that were on the initial slide. This is Jan Kurowski, our team leader. He's sitting right there, actually. So yeah, we worked on distance supervision and unsupervised learning for handwriting and speech. And this is what I'm going to show you today, like a little part of the developments that we made during the workshop. So representation learning. Everybody knows how autoencoders look like right now. And we know the qualities of autoencoders. So we know that through bottlenecking the representation, we can discard noise and keep the important information that is really important for reconstruction of the signal. But the question that arose recently is, do autoencoders promote disentanglement? Like, this is a pretty important issue right now. And what I mean by disentanglement is like, we take some input features, which is maybe a kind of a mass, and then we apply the bottleneck. And it turns out that different bottlenecks have different qualities in terms of disentanglement. And then we can either have something orderly and nice, like this bowl of soup that is made from the initial mass. But that's not what we want. This is not disentanglement. Disentanglement would be like singling out. This is like a piece of pasta, right? Thank you. And so you would like to try to single out something from that mass, or even better, like separate out all the things. The initial work that was done, like one of the pieces of work that was done on this topic was this paper, which Jan Kurowski was like a main person in, and this paper investigated different architectures of autoencoding for speech and how do they promote disentanglement. And so, first of all, I advise you to check out the paper, but the important thing is that this graph from the paper, which maps different types of autoencoders. And this is really, I don't have the time to go into details, but it's a rectangular graph, and here is like the sweet spot. So it shows you like you can take regular autoencoder, variational autoencoder, or vector quantized vector autoencoder, and they have very, very different qualities in terms of disentanglement. And now, we were working on speech and handwriting during the workshop, and this is something that I'm going to talk about right now. Speech, because it's a high bandwidth, very interesting signal, and it's still not solved how to extract in an unsupervised manner good representations from speech. And handwriting, because handwriting really resembles speech. It's a temporal signal that can be processed with the very same models. Like speech is typically processed frame by frame, so like columns by columns. And by the way, this is a spectrogram of human speech. And you can process handwriting in exactly the same manner by columns of pixels, like you would process the frames in the spectrogram. And what's nice about handwriting is the turnover time of experiments is it just goes much faster. Like you can train models in hours instead of days. And it allows you to quickly iterate through different architectures and test different bottlenecks. Because right now, we don't really know what are, like how to select different architectures, and it's pretty like experimental work. So with handwriting, we have our own corpus. We will release the corpus pretty soon. Right now, we're working out the legal procedures. So this is like the lookout for this paper here. And the corpus is of 16th century till 18th century journals and letters of conquerors, Dutch conquerors. Like one of the people on our team was Dutch, and he was like very involved in sourcing that corpus from National Archives. So we've got people like Tasman. Tasman is, by the way, the person that Tasmania is named after, and other Dutch conquerors. And this is like except from the corpus. So we got like lines of text. And this corpus is pretty nice because it has like nice volume. It has speakers that are labeled, so you can use this as a metadata for distant supervision, and it's nicely segmented into the lines. So before going to vector quantized variational autoencoder first, variational autoencoder, so one of the architectures that we are concerned with is VAE, and in VAE you try to encode into like a probabilistic representation here at the bottleneck and then decode back. You got callback library divergence, which is like the distance between the distribution that you want to encode into and your original distribution that your encoder spits out, and then you have like a reconstruction error here. We were using vector quantized VAE because it just works better for disentanglement, as was shown in Jan's paper a few slides back. And I don't want to go with the details with this, so I didn't even bother to tell you what the different symbols mean, but this is deterministic bottleneck. And what it does, it performs k-means clustering here at the bottleneck, and it just maps into a discrete set of tokens. So, so that's something that you basically should know about it. And this bottleneck gives a embedding inventory of codes. So you've got like, say 1,000 vectors, and every output of the encoder is mapped to 1. And I can show you like zoom in on this and just show you how it works instead of like explaining the equation. So say you have encoder here, decoder here, and you've got your codebook, which is the codebook in the bottleneck. And this codebook is really composed of these green dots here, and you've got areas of attraction. And the encoder spits out some vectors, which are purple dots, and you map them just to nearest centroids, basically, and then pass to the decoder. So it's really performing k-means clustering, but in a batch manner. By batch, I mean this is getting trained along with the network in batch mode. So it's really everything you should know about it. And the nice thing is that it's pretty heavy on compression. So you might think that if you got 4.32, 128 dimensional vectors, it's 4,000 bits. And if you got 1,000 codes in the codebook, you get 10 bits because you just need to say which one of the codes you are passing. So it's really heavy compression.
Do you update the codebook on the fly?
Yes, it's getting trained along with the model. And this is the basic architecture that we developed during the workshop for handwriting. So we've got pretty strong encoder, which is modeled after encoders for speech recognition models. And we've got the vector quantized bottleneck that I shown you before. And then we have a pretty powerful deconstructor, which is mainly composed of a pixel CNN. So pixel CNN is a powerful reconstructor for autoregressive reconstructor for images. We tried also WaveNet, deconvolutions, transformers. They all worked well in terms of how good the reconstruction looks like, but they didn't work just as well with disentanglement. And this is something that we are interested in. And by the way, how do we measure disentanglement? Like, I'm talking about disentanglement, how do you see like if the piece of pasta is good enough for you? So the basic methodology is to train like a small probe module, which is either linear classifier or maybe two-layer neural net, like very small module. You freeze this part of the network once it has been trained, and then just train in a supervised manner this part here and see accuracy. So if this representation was good enough, like disentangled enough, you will have nice supervised accuracy here. Of course, you know, without that, the whole model is trained unsupervised. So just to give you like a example here, so this is like the input line from the handwriting corpus. This is something that our model assigned in terms of discrete tokens, and we've got far more tokens than the characters, so it's a many-to-one mapping basically for every character. This is comparison with ground truth. So here, the upper row is the ground truth segmentation. So you can see that every character has its number and spans, you know, a number of frames. And here is the something assigned by the VQ bottleneck. And this is the reconstruction, by the way. So it doesn't look pretty good, right? It's really messy. Yeah, that's many-to-one mapping. So now the development that I want to show you here right now is that we want to learn piecewise-constant representations. So we try to use the fact that if you have like a character, it spans a few neighboring frames, right? It's a segment. We don't want to change abruptly and jump from token to token, but we want to try to say in some way that the neighboring tokens should be the same and implement that as a constraint to the model. And this is something that we got in the result. So this is, I'm going to show you how to go from this here to this. And here, again, the upper row is the ground truth, and the lower row here is something that was spit out by our model. And this is pretty accurate, like for an unsupervised system on handwriting. And if you think it's not good enough, keep in mind that for a complete system, you would apply language modeling on top of that and, you know, smooth out the prediction. So it's a basis for a really strong system if you can do that. And so for a vector quantized bottleneck, this is the quantization criteria. So basically, you have encoder outputs, X, which were purple dots earlier in the example, and then you have hue, quantized tokens, which were green, and you will try to map one to the other, like just assigning to the closest one. So you minimize the distance, right? For every output, you just have the closest centroid. So now we add the constraint. So we would like to switch infrequently, and we hard code the number of switches. By switch, I mean when you go from one token to a different one. So you might want to have a sequence of similar cues, so sequence of frames that map to the same character, and then maybe switch to a different one when you change the character. And first of all, how we come up with k. So you could try to estimate k from the data set. This is like the average duration of the character in terms of frames. And of course, it's not going to be constant, right? It varies from line to line and from speaker to speaker. This is why we enforce it as a mini batch constraint. So it's kind of similar to batch norm in a sense. So we enforce it globally over the whole batch and expect to, well, it underestimate somewhere, overestimate somewhere, and we hope that the model will work it out. And it's easy to specify as a hyperparameter, of course. Yeah, and mini batch statistics are kind of close to the statistic over the whole data set. Especially, we construct our batches in the way that we have small chunks and a lot of different sentences, so more variety in the speakers also. What's interesting is what we do during inference. So during inference, you don't want to have that. First of all, you would like to have it more deterministic and no assumption that you need other sentences or large batch to do inference. Like in batch norm, you would like to cache something during training and then reuse it during inference. So I'm going to show you the method, how we do something completely different during inference. But for that, I need to introduce or give you a refresher on Lagrange multipliers. So this is like a crucial part of the theory here. So something completely different for 3 slides, Lagrange multipliers. Lagrange multipliers is a method to optimize, to find a minima or maxima of a function under constraints. So say you want to maximize some multivariate function f that is subject to some constraints. And the method is this. You construct the Lagrangian, in which you introduce the auxiliary variables, and then you solve, saying that the gradient should be equal to 0. And what we would like to point out is that those lambdas have a special meaning here. So just so you know where you are, say that the purple f here is the 2-dimensional function that you try to find like optimum, say maximum, and g is a constraint. So you need like a maximal point that lies somewhere along g. So we're looking for maximal point along g. So let's zoom in. If you try to say that this is the optimal point, first of all, let's look at the gradient of g here at this point. So by definition, this is perpendicular to the constraint. This is by the definition of the gradient. And now let's look at the gradient of f. So f would be this purple one here. Say this is the gradient of f. We can decompose the gradient of f into components that is, one is parallel and the second one is perpendicular to the constraint. And now we need to observe that if this component here would be non-zero, then we could move along the gradient just to go towards the optimum here along the constraint line and be in a better place that is more optimal, say. So in order for this point to be the optimum, this component here should be 0. Otherwise, it wouldn't be the optimal point. Otherwise, we could just follow this component of the gradient and find a better point along the constraint contour. Sorry. So this is what should really be happening here. Those two should be parallel, and we can say this. We can express this with this equation here, that one should be like a rescaled version of the other, and this is where the Lagrange multiplier comes in. And so lambda relates how much a small change in the constraint will be reflected as a change in the cost. So it kind of reflects and balances the two. And so now we can reformulate our quantization criterion into a dual formulation with the Lagrange multiplier, where we treat this part here as a constraint with lambda. And we can actually estimate lambda during training on the data, and then reuse it during inference to balance the two costs. And then you can see like this graph here, which you can see the merges and the quantization cost. So, by merges, I mean merges between the neighboring tokens. So we first have this, let me go back here. So we perform it in the greedy manner. So we merge like a neighboring tokens here to obtain this piecewise-constant representation. And it messes up a little bit the cost, but with appropriate lambda, you can balance both appropriately. And so this has also a different formulation. You can see it as a HMM. So this part here would be the emission cost, in which you try to emission the encoder outputs, and this would be the transition cost. So you might think it's you kind of employ Markovian dynamics on this model, where you model the the hidden tokens, the quantized tokens that you obtain in the bottleneck, and they emit the encoder outputs. And lastly, some results. So unsupervised base models. Here, this column lower is better. So this is character error rate, something similar to metric used in the speech recognition. And here you've got the probed network that gives you classification accuracy, which is supervised. And using the piecewise-constant representation, first of all, gives us nice representation because you can clearly see individual characters, but then it also boosts the disentanglement by giving you better accuracy with the bottleneck, with the probe network. And so to wrap up, this is wrong. So this is part of a bigger effort, what I'm showing you here, and we've got like a pipeline of papers about the topic if you're interested in. Try to follow these. This one that I'm showing you right now was accepted to the NIPS PGR workshop as a spotlight paper. We have another one in there, 2 under review for ICASP, and then 1 about the corpus, and more coming up like at the beginning of the next year. And I guess that right now would be a good time for questions.
Thank you, Adam, for the talk.